This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is Clapeyron equation. So we're going to use the Clapeyron equation. We're going to look at steam at 120 C. We're going to find the enthalpy of vaporization and the entropy of vaporization from the Clapeyron equation. And the use of this is the HFG is the heat needed to fire a boiler, and SFG is the increase of entropy associated with vaporization. The Clapeyron equation, HFG, is temperature times the change in volume of vaporization, VFG, times the derivative of pressure with respect to temperature in the saturated condition. And that's, and a related relationship is that SFG is the enthalpy HFG divided by temperature. Now, we're going to use the steam tables because we don't have experimental data. Usually we use lab data if we're going to talk about Clapeyron for pressure, volume, and temperature. But we're going to use the tables as our lab. All right, so we need the values. We need the temperature. We've got that. 120 C is the same as 393 Kelvin. We're going to go in the tables and find VFG, and we're going to find this derivative. Let's start with the steam table for water, saturated temperature. We want to find VFG. I've got a table here, and at 120 centigrade, the difference between the VFG value is the difference between the vapor value and the liquid value. So I'm going to pull these values out, 0.8919 and 0.00106. So I'm going to say that this is the vapor value, 0.8919, and the liquid value, 0.00106. When I subtract that, I get 0.8908, and this is in meters cubed per kilogram. So that's part of what we need. We also need this derivative, dP dt in the saturated region, and we're going to approximate this as a change in pressure divided by a change in temperature. Now the temperatures I'm going to use are going to be 130 C and 110 C. So I'm going to go in there and find the pressure values associated with those two temperatures. So let's go back to the saturated table. So the pressures I'm interested in are here at 110 and 130. So 2.701 bar and 1.433 bar. So I'm going to transfer those values over here. So the upper one is 2.701 bar. And let me write that. Well, it's going to be bar. So this is 1.433. So this would be bar over the temperature change. And let me convert that to, we've got 100 kPa for 1 bar. When I compute that, I'm going to get 6.34 kPa over degrees centigrade. All right, so now I'm going to use this to compute my H. My temperature is going to be 393, excuse me. My specific volume change is going to be 0.8908. That's in meters cubed per kilogram. And my pressure is going to be 6.34 kPa per centigrade. Wait a minute, we've got a problem here. We got Kelvin over there and we get centigrade over there. But a delta T of 1 centigrade is equal to a delta T of 1 Kelvin. So those are okay. Those cancel out. I'm going to get 22 219.5 kilojoules per kilogram. Because my kilogram remains, let's look at the units here for a minute. The degrees cancel. kPa is a kilonewton per meter squared, and I'm multiplying by meters cubed. So I'm going to have meters cubed, so that I've got a kilonewton times a meter, that's a kilojoule. And that's what this is here. Okay, so that's the units. Does that value make any sense? Well, we can check this value. From the table, because the table lists HFG. HFG from the table, let's go back to the table for a moment. HFG for the table at 120C is over here. It's 2202.6 kilojoules per kilogram. Let's copy that back. Table is 2202.6 kilojoules per kilogram. And if I compare this, the difference is about 0.76% error. That's not bad. Where does the error come from? It comes from the coarseness of the delta of the approximate derivative. This is pretty coarse, 20 degrees temperature. I also want to use this to find, use this value here. SFG from Clapeyron is going to be, as I wrote earlier, HFG divided by the temperature. I'm going to use the Clapeyron value, 2219.5 kilojoules per kilogram divided by 393 kelvins. When I do that, I get 5.648 kilojoules per kilogram per Kelvin. I can check this as well using the table. But now I've got to subtract, because in the saturated table, whoops, got to scoot over here. In the saturated table, the at 120 degrees, the entropy value is only listed for the vapor value and the liquid value, so I have to subtract. So I'm going to take these two numbers, 7.1296, and subtract 1.5276. 7.1296 minus 1.5276, and I get 5.602 kilojoules per kilogram per Kelvin. I'm going to compare these guys, and the error is about 0.8%. Again, the error comes from the coarse delta T of 20K. A finer table or finer experimental data would give us a better estimate of the vaporization properties from the Clapeyron equation. Let me recap. We're using the Clapeyron equation to look at HFG and SFG for steam at a particular temperature. And we're using the tables as our laboratory. So we found the specific volume and the temperature, the pressure derivative with respect to temperature as an approximation. And the values came out within 1% for HFG and SFG. And if you remember that, we can use pressure, volume, and temperature data to get vaporization information using Clapeyron, then all will be well.